Hello everyone. Last time we saw about the classification of the GVF profiles. So now we were discussing the characteristics of the GVF profiles. And for characteristics of GVF profile, we last time derived an equation, that is the governing equation of GVF in a simplified form for a wide rectangular channel. So that form I will write down here. dy by dx is equal to, the generalized form is SB minus SF upon 1 minus q square t by g a cube. Okay, this is your generalized form. So we simplified this as dy by dx is equal to SB into 1 minus yn by y to the power 10 by 3 upon 1 minus yc by y to the power cube. Okay, so using this simplified form we will try to study all the GVF profiles. Okay, so in today's lecture we will study the characteristics of especially M profiles. Okay, M1, M2 and M3. Okay, so first we will see M1 profile. Now M1 profile will take place on a mild channel, mild slope channel. Okay, this we have seen last time. Suppose you have a mild channel, mild slope. Okay, this is your mild slope. So for mild slope, slope will be less than critical slope. Okay, this we saw last time. The normal depth line will lie here. Sorry, critical depth line will lie somewhere here, and normal depth line will lie above the critical depth line. Okay, so this will be your normal depth line. Okay, so YC will be this much, YN will be this much, and then we will have a profile here M1. Okay, if you have GVF in this zone, flow is taking place in this zone, it will be a M1 profile. Okay, so flow depth in a GVF in M1 profile, what is the first property of M1 profile? That the flow depth is greater than normal depth and flow depth is greater than critical depth also. Okay, both. Okay, fine, because flow depth is in the zone 1. Okay, and both depths are both yn and yc are less than y. Okay, so now first we will find out whether this profile is a rising profile or falling profile. This means that if the depth is increasing with x, this is your x flow direction, or it is decreasing with x. Okay, that is the first characteristic that we will try to find out. So apply this equation that we have derived last time. That is, now what is the equation? dy by dx is equal to SB 1 minus yn by y to the power 10 by 3 upon 1 minus yc by y to the power 3. Okay. Now, now see, just put qualitative values and we have to find whether dy by dx is positive or negative. Okay, dy by dx means the water surface profile slope. Okay, the slope of this line, slope of this water surface. If dy by dx comes positive, it means depth is increasing along x and flow profile is a rising profile. If dy by dx we get as negative, it means the y is decreasing with x along the flow. Y is decreasing, so that means it is a falling profile. So first we have to find out the value of dy by dx. Okay, now see, it is a mild slope, so SB is a positive number. Okay, it is a positive number, so this is positive. dy by dx is equal to, this is positive. Then we'll see what is numerator and denominator. Okay, see, numerator you see 1 minus, what is this, yn by y. The ratio is yn by y. See, yn is less than y. Okay, yn is less than y. We are dividing yn by y. So this number will be less than 1. Okay, this becomes less than 1. And if you take powers of this number, it will again become less. Okay, so suppose this number is 0.6. if you take cube, square, cube of this number, it will again decrease. Okay, that number will go on decreasing. So it will be again less than 1. So 1 minus this number will be a positive number because this is less than 1. So numerator will be positive. What about denominator? That we'll see. Again yc is less than y. Yc is less than y. Okay, so if you divide yc by y, you will get a fraction less than 1, and if you take the cube, it will again be, the magnitude will again less than 1. So this denominator also will become positive. So dy by dx should be a positive number for a M1 profile. It means that the profile is it means what? M1 is a rising profile. Okay, this is the first characteristic, that the profile is a rising profile. Now, so we know that it is rising profile, fine. Now what happens at the upstream and downstream? Okay, this we have to find out what will happen to the profile at the upstream and downstream. So at the upstream, the flow depth will at some point of time, or at some location where the GVF is going to start, the gradually varied flow is going to start from some location. Suppose this is location. At this point, GVF is going to start above, and beyond this point upstream, what is the flow? Flow is a uniform flow. Depth is normal depth. Okay, y is equal to yn. Okay, so this is far upstream. So at far upstream, the depth tends to the normal depth. Okay, depth tends to normal depth. So how the dy by dx approaches that depth, that we will see. So y tends to yn. So dy by dx, if you calculate at this zone, okay, when the flow depth is almost equal to normal depth, it is not exactly equal to normal depth, because then the flow will be a uniform flow itself, but there is a zone where the flow, there will be a point where the flow depth is just equal to the normal depth. There what will be the dy by dx? See, y is equal to yn. So what will be the value of dy by dx? SB 1 minus, see, SB is positive. Okay, then what about the numerator? 1 minus yn by y to the power 10 by 3. Now this y is almost equal to yn. Okay, so this number becomes 1. Okay, so 1 minus 1 raised to any number is again 1, and 1 minus 1 is 0. Okay, so this becomes 0. So ultimately dy by dx becomes 0. Okay, even if you take the numerator also, but you have denominator also. In the numerator you have 0, so entire quantity will become 0. So slope is equal to 0. Now what does this mean? Dy by dx is 0 means that slope is almost 0. So change in flow depth, as the flow is moving ahead or taking place in the x direction, the change in flow depth is very, very, very slow. That means that flow is almost tangent to the normal depth line, or we technically correct language we say that flow is that M1 is profile is asymptotic to NDL, normal depth line, at the upstream. Okay, at upstream M1 profile is almost asymptotic to the NDL. Okay, and what about the downstream? At downstream, y is equal to the control section. What does this mean? Y is governed by control section. Y is equal to actually control section depth. How? See, to create M1 profile, some or the other barrier will have to be placed here. Okay, some or the other obstruction will have to be placed. Because of this obstruction, when the flow is taking place over this weir or some spillway, this becomes a control section. Okay, this becomes a control section. So depth here is a fixed depth y. This depth here is fixed, and it depends upon the type of structure, properties of that structure. So this becomes a control section. So at the downstream, depth is just equal to the depth at the control section, whatever you are providing. Okay, so these are the characteristics of M1 profile. Okay, and what is an example of M1 profile? On a mild slope, if we are providing a barrier, okay, if we are providing barrier on a mild slope, then we can get a M1 profile. Okay, at the upstream it will be almost asymptotic to the normal depth line, and downstream depth will be controlled by the governed by the control section. Okay, so this is about the M1 depth, M1 GVF profile. Now we'll look at the M2 profile. The same method we can apply to understand the characteristics of M2 profile. Okay, so M2 profile will take place where we will have again a mild slope. SB will be less than SC. Normal depth line will be somewhere here, critical depth line. Then again a normal depth line will lie above this critical depth line. Okay, and flow is taking place in this region, suppose. Okay, so this is your YC and this is your Y. Flow depth of this profile, this will be M2 profile. Okay, now see, the flow depth will be less than the normal depth. For M2 profile, the flow depth in the GVF zone will be less than normal depth but greater than critical depth. So Y is actually less than Yn, but Y is greater than Yc. Okay, so what will be the characteristics of the profile? Calculate the dy by dx again. Dy by dx is SB 1 minus Yn by y to the power 10 by 3, 1 minus Yc by y to the power 3. Okay, now what will happen to SB? SB is a positive number. Okay, what about this numerator? 1 minus, what about this fraction? Yn by y. See, Yn by y. Yn is greater than y. Okay, so this number will be more than 1. Greater than 1. Okay, and again raised to 10 by 3. It will again increase. So 1 minus a higher number will be a negative number. Okay, so numerator will be negative. What about denominator? See, Yc is less than y. Yc is less than y. So this number is less than 1. So 1 minus this number is less than 1 and raised to 3, it will again be less than 1. So 1 minus less than 1 will be positive. So the entire dy by dx will become negative. Okay, therefore M2 is a falling profile. M2 is a falling profile. Why? Because dy by dx has come out to be negative. So y has to decrease with respect to x. Okay. Now what will happen at the upstream? At upstream, again M2 profile, again the flow depth tends to normal depth. Okay. Again at the upstream the flow depth is going to be almost equal to normal depth. So dy by dx will be, it will be, see, SB is positive. Okay, now flow depth is almost going to be equal to Yn, so again this will be equal both, so this will be 1, so 1 raised to 10 by 3 will be 1, so 1 minus 1 is 0, so entire thing will become 0, divided by anything, still it will become 0. Okay, so 0 means we have seen that the this flow profile is asymptotic to the normal depth line. Okay, so it will be something like this. Okay, at the upstream. So at the upstream, M2 is asymptotic to normal depth line. Okay. Now what about the downstream? At the downstream, y tends to be equal to yc. Okay, y will be almost equal to yc. Okay, it will meet the critical depth line somewhere. So what will happen to your dy by dx there? Slope of this line, or what will happen to the slope of the profile? So slope of the profile, will see what will happen. Y has become equal to yc. Now, so what you get, SB is positive, but what about the denominator? We are getting 1 minus yc by y. So this is 1. Okay, because yc and y both are same, so this will be 1. Cube of that number will also be equal to 1. So this will be 0. Okay, so this will become infinity. Okay, because anything divided by 0 will become infinity. So dy by dx, the slope becomes infinity. Infinity slope means practically how we can imagine that when the flow is approaching critical depth line, the slope is very high. Infinity means the change in depth is very high for a small change in x. So for small change in the distance, the change in flow depth is very high. So drop in the flow depth is very high. So we show it like this, normal. So at downstream, M2 is normal to critical depth line. Okay, so this is the characteristic of an M2 profile. It is normal to this critical depth line. So at the upstream, it is asymptotic to NDL, then it is falling, and it will fall normally at the critical depth line. Okay, so these are the characteristics of M2 profile. And what is an example? Example of M2 profile will be if we provide a straight drop like this on a mild channel. Okay, on a mild slope, if you provide some straight drop, your critical depth line is this, normal depth line is this. Okay, so what will happen? Flow is coming by normal depth, but it will start to fall. It will go like this. Okay, so you are going to get a M2 profile. Okay, on a drop on a mild channel. Okay, this is an example. Now lastly, we will see the characteristics of M3 profile. So M3 profile, how it will behave, that we will see. M3. Okay. Now M3 profile, again it will take place on a mild channel. Okay. But now there is a difference here. This is critical depth line. This is normal depth line. So M3 profile will lie in the third zone. So this is the third zone, above the channel bottom, below the critical depth line. So it will lie somewhere here. So this will be your M3 profile. Okay. What about the depths? So this is the flow depth. Flow depth is less than YC and YN both. Okay. So for M3 profile, the characteristic is that depth is less than YC and depth is less than YN both, normal and critical depth. The flow depth is less than normal and critical depth. Okay. So what happens to your dy by dx? See, SB is again a positive number. Now what happens to 1 minus yn by y? Now yn is greater than y, alright? Yn is greater than y. So this number is more than 1 raised to 10 by 3. Again it becomes more than 1. Okay. So 1 minus something more than 1 is a negative number. So numerator becomes negative. What about the denominator? again you look at this yc is again greater than y. Okay, so this number is greater than 1, cube of that number is again greater than 1, and 1 minus this number is again a negative number. Okay, but negative divided by negative, both numerator and denominator are negative, so this dy by dx entirely becomes a positive number. Okay, so it is a rising profile. Therefore M3 is a rising profile. Okay, M3 is rising, so we can plot that here. So this is a rising profile. Okay, now what will happen at the downstream? First we will see at the downstream. At the downstream, flow depth almost tends to critical depth. Y tends to YC. This will meet the critical depth line. Okay, this GVF profile will meet the critical depth line. So again dy by dx will be, see, this is positive, so it will be positive. Okay, but y will be equal to yc, so this will be 1, so 1 minus 1, this 1 cube will also be equal to 1, and 1 minus 1 is 0. So something divided by 0 will become infinity. Okay, so your slope is becoming infinity. That means the flow profile will be normal. Okay, normal to this critical depth line at the downstream. So M2 is normal to CDL at the downstream. Okay, and what will happen at the upstream? At upstream y tends to 0. See, theoretically this is not actually practically this is not possible that we will get a 0 depth will always be a positive, some positive number, but here theoretically depth can go equal to 0. So when it goes equal to 0, your dy by dx becomes, if your y is 0, then something divided by 0 is infinity, so we are getting infinity, same at the denominator, infinity by infinity, so this is undefined. Okay, so the slope is not defined. For theoretical slope cannot be defined for this condition. Okay, practically what will happen at upstream, the flow is governed by some, now this is a supercritical flow, so it has an upstream control section, so it will be governed by some control sections. For example, a sluice gate. Okay, so flow will be taking place below a sluice gate, so that depth will be controlled by the upstream control section. Okay, so this is about the M3 profile. What is an example? Just what I draw there. On a mild slope, if you put a sluice gate and the depth, sluice gate opening is below the normal depth line. If you keep the opening below the normal depth line, flow is going to start from here. Okay, so the profile that will be formed is a M3 profile. Okay, because we are in the zone 3, slope is mild, we are going to get an M3 profile. It is a rising profile. Upstream depth is governed by the sluice gate, downstream it will meet the normal depth line normally. Okay, so this is all about the characteristics of mild slope profiles. In the next classes we will see characteristics of other profiles also. Thank you.